All right, so we're ready now for chapter 6. And so we're going to be doing some extremely important material in this chapter. We're going to introduce two concepts that will be important throughout the rest of this course and also stats decision making. What is this all about? Well, we're going to introduce the concept, as you can see, of random variable and what's called the probability distribution. So first things first, what exactly is a random variable? Well, first of all, when we assign a random variable or define one, we're assuming that some type of random experiment is taking place. And as we know, that means that there's a process going on that generates some kind of random outcomes. What's happening here is that we're taking all those possible outcomes and simply assigning them numbers. So now for many cases, it's much more convenient to deal with numbers than, let's say, heads and tails, if we're flipping a coin or, whatever the case may be. It's very helpful to have numbers assigned to the outcomes of an experiment. Part of the reason for that is so that we can calculate probabilities with formulas rather than having to count up all the elements in the sample space as we did in previous chapters. So now we're going to go back and look at this example that we've seen before. A die is rolled twice. And we're only focused on whether or not the outcome is even or odd. We don't really care what the individual numbers are. We're only looking at odds and evens. Now, suppose that in this experiment, we define the random variable x to represent the number of times that an even number turns up during the course of this experiment. So first things first, the sample space is going to consist of only 4 elements, which are, of course, EE, EO, OE, and OO. So now what we're looking for is the number of evens in each of these outcomes. So we're going to put this together in a chart, and we'll see that in the first case, EE, x is equal to 2, because there are 2 heads. Remember, x is the number of heads. Now, in both of these cases, there's exactly 1 even number, so x is equal to 1 in both of these cases. And then finally, OO, there are no evens, so x is equal to 0. So all we're doing is taking each possible outcome of this experiment and assigning it a number, although we are the ones who specify how that number is determined. And I think, well, you'll see when we're done here that it's always easier to have numbers than letters, like EE, EO, OE, et cetera, et cetera. So we've already seen that each of these outcomes is equally likely. So if that's the case, the probability that x equals 0 is the same thing as the probability that we end up with OO. Any way you look at it, this probability is 1/4. Because it means the same thing. X equals 0, getting OO when we roll the dice twice means the same thing. And you recall that each of these outcomes has a probability of 1/4. And that's because each die has 3 even numbers and 3 odd numbers. So each of these individually has the same probability which is 1/4. And that's because there's 4 possible outcomes, each of which is equally likely. All of these have to add up to 1. Now, what about 1, though? This is an interesting case because the probability of x equaling 1 is the same thing as saying the probability of getting EO or OE, which can be written as the union of EO and OE. And because these are mutually exclusive outcomes, we can use the simplified addition rule to write this as the probability of EO plus OE, which is 1/4 plus 1/4, which is half. That's fine. The probability that x equals 1 is 2/4 or 1/2. And then finally, x equals 2. That's pretty straightforward because this is the same thing as saying x, the probability of getting EE. There's only one way that can happen. And so we end up with a quarter because these two represent the same outcome. So now we can gather these up into a nice little table. In fact, here it is. So already we've defined two important ideas. X, remember, is a random variable because it assigns numbers or numerical values to the outcomes of our experiment. And this table represents what we'll call a probability distribution. And all that means is that we're taking each possible value of x and assigning it a probability. So we go from the outcomes of the experiment to the values of x to the corresponding probabilities. And it's this that we're really interested in. The probability distribution will make it easy for us to calculate whatever probabilities we need. Okay. And again, you'll see it'll be easier than directly dealing with EE, EO, OE, and OO. Now, one thing we want to point out here, though, is that among these probabilities, all of the probabilities that we see must be non-negative. In other words, no probability can be negative. The probability of any event, A, let's say, is at least 0. And the probabilities of all the possible outcomes of this random experiment have to add up to 1, which is equivalent to saying the entire sample space has a probability of 1. All of them add up to 1 because one of them must be true. Whereas in this case, when I roll the dice, one of these outcomes must happen with certainty, which means that the entire probabilities, all the probabilities have to add up to 1. All right, so now that we've got those definitions out of the way, one more definition I almost forgot. When we have an experiment like this, where there's only a finite number of possible outcomes, like we have here, there's only 3, we say that this is a discrete probability distribution, where discrete means basically the same thing as finite. It means that we do not have an infinite number of possible values for x. Although now you might say, well, how could that possibly happen? In chapter 7, we will see what happens when we have an infinite number of possible outcomes. When x can assume an infinite number of possible values, it has, of course, a different name. It is, that means the corresponding probability distribution is said to be continuous. Okay, so in other words, let's quickly summarize that. Those are the two cases we could potentially run into. So when we classify probability distributions, discrete, only a finite number of possible outcomes, continuous, an infinite number. An infinite number of possible outcomes, which we will not consider until chapter 7. Okay. In this chapter, we'll focus our attention on discrete probability distributions only. Now, here what we're going to do is introduce some ideas that we've already seen before. We know that from your earlier chapters that when we were dealing with samples and populations, there were summary measures that we used to describe their properties. They fell into the 3 different categories measures of central tendency, measures of dispersion, and measures of association. So we remember how that works. Now, something similar will be happening here when we're dealing with probability distributions and random variables. It turns out that we can also define summary measures for random variable, only the terminology is slightly different. Okay. You have to be careful in statistics with terminology because, we can often have multiple names that really refer to the same concept. So when we're dealing with a random variable or a probability distribution, the summary measures that we just described are referred to as moments. I don't know why, but that's how it's done. Okay, now for our purposes, we're only going to focus on the following. We have the expected value, which is just another name for mean. And then we have the variance and standard deviation, which correspond to exactly what we saw in earlier chapters. They are both measures of dispersion. And furthermore, the standard deviation is the square root of the variance, as it was in chapter 3. So, how are they calculated, though? What's going to be different here, unlike with samples and populations? What we need to do here is take into account probabilities. This is something new. So the formulas that you'll be seeing will include probabilities. So the expected value is the mean. Sometimes it's called the first moment. And so here's how this formula looks. EX stands for expected value, of course. Well, not of course, that's just how it's defined. X is the random variable that we're studying. X is some discrete random variable. It doesn't matter how it's defined, as long as it's discrete. On the right-hand side, what we're seeing here is that there's all these different possible outcomes of this experiment, which we'll call xi. Each one has a corresponding probability. So here we're seeing there are n possible outcomes of our random process. Each one will generate an xi, and each xi has its own corresponding probability. So based on our knowledge of the summation operator, what this is telling us to do is multiply out all those outcomes by the probabilities and add them up. Okay? So this is, remember what we did before. We added up the x's, but now what we did was divided by n. Now, I'd like to point out that this is equivalent to multiplying by 1 over n. So this probability corresponds to this 1 over n in the calculations. It's as if the sample elements were all equally likely to be chosen. Okay, it's equivalent to that. Now, that's not going to necessarily be true, but so we're calculating, and by the way, this could be formally defined as a weighted average. Where the probabilities are the weights. Okay, so this actually is a weighted average where the probabilities are the weights. All right, anyway, so let's look at that experiment again. Now, let's go back to our table. And these are the values we have. So let's think of this as x1, x2, and x3. These are all the possible outcomes of this experiment. This would therefore be px1, px2, and px3. So to come up with the probability, the expected value of this x, what we're going to do is literally just multiply all these x's by their probabilities and add them up. And so when we do that, this is what we'll get. Okay, so this is the first x. This is the probability of x1. This is x2. This is the probability of x2. This is x3, and this is the probability of x3. When you multiply those out and add them up, it's 1. Now, how do we interpret that? Well, remember what this refers to. This is the expected number of evens that turn up when we roll the die twice. So in other words, we're saying that on average, when we roll the die twice, we'd expect to get a single even number. All right, so remember from way back in the table, we chose X to represent the number of evens that turn up. Now, we could have done it the other way around, but since we chose X to represent the number of evens, then that means that 0 means no evens. This is the result of getting two odds. This is either EO or OE. And this is two evens. And then these are the probabilities. That could be thought of as the probability of OO. This is the probability of OE plus the probability of EO. And this is the probability of EE. Multiply them out, add them up, and we have our expected value. Okay, now the variance. Now again, the formula for the variance will be somewhat similar to what we saw for the population variance, except now we have probabilities involved, which we did not have before. This one is often called the second central moment. We'll see why in a second. The word central means that we're subtracting the mean from each term. And this again is a measure of dispersion, as we know. And so that's the formal definition, but the actual formula that we'll use for calculating the variance is a little bit different. And by the way, if you notice, we're using the same notation that we use for populations. This sigma squared can refer to either a population variance or the variance of a random variable. Now, you might say, well, how do we know which it is? It should be clear from the problem that you're working on. Right, so I guess that's the logic. We didn't need to create a new variable because it should be clear which type of variance we're talking about. So what you're going to do here, and by the way, this might look familiar to you. Remember, the population variance requires us take each X, subtract the mean, square the differences, and add them up and divide by n. And I would also like to point out once again that this is equivalent to taking this squared sum of squared differences and multiplying by 1 over n, which corresponds to this probability. So it's a very similar process to what we used for populations. Now, remembering that the expected value of X for the die rule in the experiment turned out to be 1. Here we have X1 minus the expected value of X squared, the probability of X1. Here we have X2 minus EX squared times the probability of X2. And then finally down here, we have X3 minus the expected value of X squared times the probability of X3. So in a case like this, what you want to do is first evaluate the differences and then square them. Then you multiply by those probabilities, add them up, and you end up with a half. Oh, okay. So it's a lot of work, but it's not that conceptually difficult. And it's likely, it's not radically different than what we did with populations. Now, of course, the standard deviation, you remember that from 3. This standard deviation is the square root of the variance. That never changes. Okay. So we use the standard deviation, and that's always going to be the square root of the variance, regardless of what type of standard deviation we're calculating. So that implies, whoops, that we can actually write it like this. Because it's literally just the square root of the variance. So in our case, we already know the variance to be a half, so we take the square root, and guess what we end up with? radical 1/2 is approximately equal to 0.7071. So that's the standard deviation of our die rolling experiment. So you can see it's a very similar idea to what we did with our measures in previous chapters. Now, it turns out, now I did say that this distribution, this probability distribution that we created, is a very simple one, is a discrete probability distribution because there's only 3 possible values of X. This one is very limited in usefulness, though. There's 2 basic discrete probability distributions that we'll need on a regular basis in business applications. And so I'm going to introduce them to you. The first one is called the binomial distribution. And the second one is called the Poisson distribution. And so each one is generated by a different type of random process. And what will be different now is that instead of calculating these probabilities with a table, or by counting the number of ways outcomes can occur, we have an actual formula. Now, here's some good news, though. For the first time, well, I guess I shouldn't say the very first time, but now all of a sudden, our calculators will be even more useful than ever before because they have functions built into them that are designed to help us calculate probabilities for many distributions, including the binomial and the Poisson. So while the formulas look very scary, you can do these with your calculators as well. And they're not difficult at all. So now the binomial distribution gives us a hint what it's all about with the name. You can see this prefix bi. Bi, of course, means 2. Like bicycle, for example, okay? So in order for us to use this distribution, our random process or random experiment has to have 3 key properties. Otherwise, we have to use something else. Number 1, the trials have to be independent of each other, meaning that the outcome of one trial does not affect the outcomes in the other trials. Number 2, each trial can only have 2 possible outcomes. And we're going to call them success and failure. Now, this, by the way, this is the origin of the name binomial. 2 outcomes, binomial. So just as a quick example, if we're flipping a coin, we could let heads be success and tails be failure. Or if we're picking cards from a deck, red could be success and black could be failure. Or if we're picking pieces off of a chessboard, white could be success and black could be failure. What else? Oh, there's a million possibilities. Or if we're picking numbers at random, odd could be success and even could be failure. So there's a lot of situations out there that could lend themselves well to being described by this binomial distribution. And finally, the probability of success, which in this book will be represented by the Greek letter pi, is a constant from one trial to the next. In other words, it doesn't change. Like with a coin flipping experiment, the probability of getting a head is always a half, regardless of how many times you flip the coin, how many times heads is turned up. Each flip is independent. Each flip only has 2 possible outcomes, and the probability of success is always the same. So the process of flipping a coin and observing whether each outcome is heads or tails could be or does qualify as a binomial process or a binomial experiment, and therefore we could calculate the probability of a given number of heads with the binomial distribution. Now, this will prove to be very helpful. Like if I only flip the coin a couple of times, it isn't going to take much work to figure out the probability of getting, let's say, no heads or something like that. But what if I flip the coin 10 times or 20 times or 50 times? Then having a formula starts to become a huge benefit. So while we could theoretically continue to calculate probabilities using tables and counting the number of outcomes, we don't want to do that too much longer because that's going to be very clumsy if we have a large enough number of trials. All right, now we're going to use the following scary looking formula to calculate binomial probabilities. And so we already know what all these terms actually mean. X, capital X, is a binomial random variable, and it could refer to, for example, the number of heads that turn up when we flip the coin 10 times. So we're going to make a distinction between capital X and lowercase x, which refers to the number of successes. So if we're trying to figure out, let's say we flip the coin 10 times and we want to know the probability of getting 4 heads, then lowercase x would be 4. N is the number of trials. And as I've already mentioned, pi is the probability of success. Which if you define heads as success, that means this is the probability of heads. And that implies, because there's only 2 possible outcomes, that 1 minus pi is the probability of failure. Okay. So now, the only thing we still need to explain is what is this? What is this thing? Well, it's actually shorthand notation for a very interesting concept that we will describe in stages. What we're doing here is delving into an area or a branch of math called combinatorics, which is the science of counting. You may have seen this in a finite math class. In fact, I think you have to take finite math at Fordham, especially if you're in the Gabelli School of Business. So what we're about to do may be review, but that's okay. So first things first, this is what that term represents. So you look at this and you say, wait a minute, what are these exclamation points doing here? This exclamation point is a mathematical operator. We call that n factorial. And of course, that implies that x with an exclamation point is x factorial. Okay, now what does it mean? Good question. Well, here's how it is formally defined. First of all, it's only defined on non-negative integers, meaning 0 or positive integers, in the following way. 0 and 1 factorial are both equal to 1. After that, that's where it gets interesting. And by the way, this is sometimes known as a recursive definition because each value depends on the previous values. 2 factorial equals 2 times 1, or 2. 3 factorial is 3 times 2 times 1, or 6. 4 factorial is 4 times 3 times 2 times 1. Okay. So in general, what you've actually got here is this. Okay, so no matter what n is, you're multiplying n by its previous value, n minus 1, n minus 2, and you keep stepping back all the way back to 1. What is it for? It has at least one very important application. Let's look at this scenario. You move into your room in September and you have room on the wall for 3 of your posters. Let's say you have 3 posters and you got room to hang all 3 of them. And here, these are your favorite things in the world: the Yankees, Salvador Dali, and statistics. So what we're going to do is try to figure out how many ways can you hang your posters. In other words, this is your wall. Oh, let's say here's your top of your bed there, your nightstand or something. Here's the wall. Exactly enough space for 3 posters. So the only choice you have here, you can't have more posters, although you could have less. Let's say you want to put them all on. Otherwise, you'll have blank space and you don't want that. The only option you really have, or the only choice you have, is what order to hang them from left to right. How many ways can you hang these posters? Well, the first thing we're going to do is simply write them out. Okay, we're going to abbreviate these as Y, D, and S. And so if you go through the list, you'll see that these are the 6 ways you can hang those posters. There aren't any more. That's it. Now, because we're taking all 3 posters and just changing their order, each one of these is referred to as an arrangement. So you have 6 arrangements are possible with 3 objects. It doesn't matter what they are. They could be posters, they could be paintings, who knows, they could be anything, but if you only have 3 of them, there's only 6 ways to arrange them. Now, what we had to do here to figure that out was write them all out, and that can get very cumbersome if we had even a relatively small number of posters, like 5 or 6. Luckily, it turns out we can do this very easily with the factorial operator. In other words, the number of possible arrangements of n objects is equal to n factorial, and that's all there is to it. So in other words, with 3 posters, can be arranged in 3 factorial, which is 6 different ways. Wow. So it's just 6. And we already proved that, of course, by counting them out. But if we understood this rule already, we wouldn't have needed to bother even with that. We would have just said, oh, it's just 3 factorial. And so what that implies is that with 4 posters, there are 4 factorial equals 4 times 3 times 2 times 1. There's 24 possible arrangements or ways of hanging them. With 5 posters, you can see this is growing very quickly. $120. And it grows very, very quickly. So that's one you don't want to count it yourself. Like 5 posters, even 120, I don't want to count those all. Now, this is our first opportunity to learn some of the cool features on your calculator. Now, this is for the 83 and 84, and that includes, by the way, the 84, the CE, which is a relatively new version. Yeah, this one. This one, it says the 84 CE plus. It's the same as the original TIA 84, except the screen is different. And they've added a few new features here and there, not that many, but you have to keep your eyes open because it's not exactly the same as the 84. There's a few improvements, but for the most part, they're almost identical to each other. They also have an 89 and an Inspire. I don't really know how to use either one of these. So if you have one, you'll have to look it up on Texas Instruments website if you get stuck. Now, here's the instructions for calculating factorials. Now, let me just confirm that this is exactly the same on the CE. You start with 3. Then you hit the math button, which is it's way in the upper left-hand corner there. And then that should bring up a menu. In fact, a bunch of menus. See, I know you're looking at it backwards, but you can see there's a lot of menus. You want the one you want is the one that says PRB, which is, oh, see now, I knew it. I just got this one during this spring, and I just got it out of the box like the other day. I just noticed that they made this new change. You notice on this menu, it says oh God, it's backwards, but it says PROB. On the TI-84, regular TI-84, it just says PRB for probability. So it's the same menu. Oh, I don't know why they have to do this. Then you scroll down to entry number 4, which is that factorial operator. If you hit the enter button, it says in the window 3 factorial, if you read that backwards. Now you hit the enter button again, and it says 6. Yeah, backwards 6. That's what it is. All right, so try that on your calculator. Whether it's the 84 or the 84 CE, you should have no trouble figuring it out. Okay. Now, I did say, though, that in this binomial formula, this circle term is not just factorial, but it's n factorial over x factorial times n minus x factorial. That whole expression has its own interpretation. Although it consists of factorials, the entire term has its own unique interpretation. So we're going to introduce the concept of combinations. So unlike with arrangements, where you're simply taking a group of objects and changing the order, here you're actually choosing from a larger collection. Okay, in other words, I might say I want to pick, let's say I have 10 posters at home and I pick 3 of them to bring with me to school. That is different than arrangements. With arrangements, you're taking all 10 of your posters and just changing the order. Here, I'm picking 3 of my 10 posters. Now, the question is, how many ways can I do this? Let's say that, for example, even before I move in, I know there's only room on that wall for 3 posters, but I have 10. So before I leave for school, I pick 3 of them, the 3 that I want to see all semester long out of the 10. The question is, how many choices do I have? Each choice in this case is known as a combination because the order in which I pick my 3 posters does not make any difference. Okay. And so imagine that we did pick out of 10 posters, Yankees, Dolly, statistics. So the order in which I selected them out of my group of 10 makes no difference. So each choice is referred to as a combination. And that formula that we saw tells me how many combinations I can create when I choose X objects out of N. So it's a formula for calculating combinations. So now let's look at an example. Here's a fun example. I'm going to head down to my local Haagen-Dazs, and I find out that they have a special offer going just for today. Assuming I buy an ice cream, of course, they'll give me any 3 toppings I ask for $1. They have 5 to choose from: gummy bears, marshmallows, chocolate chips, whipped cream, and Oreos. Now, the order in which I pick them is actually irrelevant because no matter what order I pick them in, they're going to pour them on the top anyway. You would not be able to tell the difference between 2 ice creams with the same toppings that had the toppings chosen in a different order. So we are looking at combinations now. The question is, how many ways can I choose 3 toppings out of 5? Good question. Well, again, as always, one of the options I have is to simply write them all down. I'll tell you what. So it looks like here I was just trying to introduce the idea. Let's actually do this. Just to give you some experience with this formula, Yeah, I guess this was meant to be just an example of what a combination is, but I want you to actually see how this is done. That means that I've got 5 toppings to choose from, and I can pick no, I want to be consistent. Yeah, X. Okay, good. I just want to make sure I'm being consistent here. Yeah, that's right. Now I just have to substitute for these combinations, or factorials, I should say. So 2 factorial is just 2 times 1, or 2. 3 factorial is 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. So we'll have 120 over 6 times 2, or 10. So that means there's 10 ways I can choose those toppings for my ice cream. So I had 2 options. I could either draw up a list, which would have taken a while, or just simply use this formula. Now, I'm going to give you a helpful hint. There's a function built into this calculator that'll do this directly. And it's actually in the same menu as the factorials. So remember, n is 5 and x is 3. So what you're going to use, type 5. And then we have to go to the right menu. Math, probability. Same as before. So start with the 5. Then we have math, probability. Scroll over to probability. Scroll down to number 3. NCR. That stands for number combinations. And when you choose that, you're going to get, it's going to say now on the screen. Now, this one's a little different, I think, than the TI-84. It's going to ask you to provide the 3. And then you hit enter. So notice, you see, you're supposed to fill in this blank with the 3. On the 84, I think you just type it. But either way, you type in the 3, enter, and you're going to end up with 10. Okay, that's 10, just as we calculated algebraically. All right, so the calculator agrees with us that the number of combinations is 10. All right, now. Here's another example. But this time, it's a little different. Because the order in which I make my selections will matter. When that happens, each individual choice is referred to as a permutation. Okay? So let me summarize that here. So combinations, the order of selection does not matter. With permutations, the order of selection does matter. Okay, now I'm going to show an example, and you'll see why the order does matter in this case. So imagine that we decided because everybody wants this anyway, that altogether there's 20 students who decided that it's high time that we have a statistics club at Fordham. Now, there's just one problem. In order to follow the rules of the school, the club must have a president, a vice president, and a treasurer. Okay, that's the rules. All right. Otherwise, you can't have your club. So let's say I've become this faculty advisor. And so I know that I've got to have a president, a vice president, and treasurer. And I ask the students, well, who wants to be the president? Who wants to be the vice president? And who wants to be the treasurer? And the students can't seem to agree among themselves who gets to be which, to fill which office. So I decide that I will randomly pick 3 names or numbers, actually. There's 20 students. I'm assigning each student a number. And I'm going to randomly pick the 3 numbers, and the order in which I select them will determine first chosen is the president, the second chosen is the vice president, and the third one is the treasurer. So the order matters, because if I choose 137, that's very different than choosing 713, even though they're the same numbers. With 137, student 1 is the president, student 3 is the vice president, student 7 is the treasurer. With 713, student 7 is the president, 1 is the vice president, 3 is the treasurer. The order does matter a great deal now. So the question is, how many ways can we fill these positions? Oh my God. Well, it turns out that for permutation, the formula is a little bit different. So remember, with combinations, we have n factorial over x factorial, n minus x factorial. With permutations, n factorial over n minus x factorial. You see the difference right here. We do not have this extra x factorial with permutations. So for the example of the club, remember we had 20 students. N is 20 and x is 3. So the number of ways we can fill those positions it's in here. Okay, so it's going to be okay, so if you plug in those numbers, I'll just tell you what it is. And then I'll show you how to do this in the calculator. Ooh, 6840. Now, you can do that directly, or what you can do is follow the menus like we did before, but this time it's for permutations. Let me show you how that's different. It's only one difference. So for permutations, n is, in this case, n is 20 and x is still 3, actually. So what you're going to do is go to that same menu, math. Actually, no, you'll start with 20. Then you'll have math. So you're coming back to the same menu we've had already a couple of times tonight, the probability, but now this time you pick number 2, which is NPR. And then you supply the 3. Okay, so you hit NPR, hit the 3, enter again, and it gives you the 6840. All right, so that's how we calculate permutations. Now, we don't need permutations in this chapter because the binomial distribution formula only includes combinations. But I think it's important that you have a complete picture here of the different concepts that we need from combinatorics, which is to say the arrangements, combinations, and permutations. But really, the one that we are focused on here is the combinations because we need those for the binomial distribution formula. Now, there's an interesting historical episode here that we should discuss. There's actually a video for this too, but I kind of like to save this for another time. We have several good examples coming up here for combinations and permutations. But ultimately, all they're meant to do is, at least for the combinations, is plug them in to the binomial formula so we can calculate binomial probabilities. Okay, so let me go back and show you that formula again. So in other words, what this discussion we've just had is all about is that interesting term there. And it's, oh, by the way, I forgot to mention this in English, that term is sometimes pronounced N choose X, which simply means we're choosing X objects out of a collection of N. If the order matters, then they're permutations. If the order doesn't matter, then they're combinations. But either way, we're still choosing X objects from N objects. Okay. But this is still just a piece of the binomial distribution formula. That's what we're building up to here. So what I'd like to do, I guess, because we got plenty done tonight, is to run through some more of these examples. I want you to see the fun example, which is based on a historical episode involving Ronald Fisher, who lived at the beginning of the 20th century in England. I believe he taught at Cambridge, but he was a very famous statistician, and he had this incident where he was attending a tea party, and what happened at the party gave him an important insight into probability theory that he was able to turn into a series of papers, and some important discoveries came as a direct result of this case. So I want to go through it fairly carefully and explain to you exactly what happened. But and we have other examples to look at here too. But finally, what we're building up to is the binomial distribution. And it turns out that all of this work is important, but the calculator is so helpful that there's yet another formula in here that can help us with our binomial probabilities. So by the time this chapter is done, we're going to have a very good grasp of many different key formulas that this calculator can provide us with. And going forward, we're going to use the calculator quite often from this point forward. So hopefully you've got one of these. And so we're going to have a lot, or get a lot of use out of it. So I think we'll stop right here. And when we pick it up again, we'll look at this case study with Ronald Fisher. We'll do some more examples of combinations and permutations, and then we'll do some binomial probabilities. Okay. All right. So I'll see you all next time.